Really a pleasure to be here with you for the next 2 days. I will share my screen with you, and I hope you can see my slides.
Yes, we can see.
Wonderful, thank you. So we have 85 participants, and you are organized into 14 teams, which is excellent. The teams are mixed, so we have from DADC and from industry, and we will have 2 days and then a third day, which will be in Japanese only. The first day today, the topic is an overview of engineering systems. We will also discuss the importance of analyzing your stakeholder network. And I'm really, really pleased to be presenting to you with my colleague, Dr. Brian Mosier. He will take the second part of the lecture this morning. In the afternoon, we will then have some exercises that will apply the concepts from the morning to practical examples. And this is where you will be working in your groups, but you don't worry too much. I hope you're not worried because we have some wonderful TAs who are also here to help you along with the exercises. We will be collecting your responses from the exercises. And so please make sure you submit them before the end of each day. Tomorrow, the topic will be a little bit more complex. We will talk about system life cycles. We will talk about technology life cycles and also to explore the architectural spaces. The mission of DADC, of course, is an exciting one, but also a very challenging one. And we need to think about architectural design of not just information systems, but all systems in society in very new ways. And so we will be exploring trait space analysis and also how new technologies replace older technologies through what we call the interlocking S-curve model. We will also have then exercises in the afternoon tomorrow. And then on the third day, which will be January 14th, it will be all in Japanese. There will be some more discussion, particularly of Society 5.0 and the mission of DADC. So this is just a short overview of the program over the next 3 days. So with that, why don't we get going? And so the first thing I would like to do is tell you a little bit more about myself. So my name is Olivier de Weck, and I go by Ollie for short. And I'm originally from Switzerland. I was born in Fribourg in Switzerland, which is in the western part of Switzerland. It's a half German, half French-speaking city. I studied industrial engineering at ETH in Zurich and came to the United States in the 1990s, first in St. Louis at McDonnell Douglas, which is now part of the Boeing company, and then joined MIT for my master's and PhD from 1997 to 2001. I joined the faculty in 2001 and have been there for 20 years. I do believe it's very important for people in academia to spend time either in government service or industry and vice versa. So I had the pleasure to be on leave from MIT for 2 years, 2017 and 2018 in France at Airbus, who is now the largest airplane manufacturer in the world. And I served there as senior vice president for technology planning and road mapping, essentially looking at the long-term future of aviation and aerospace in general. I will also mention that I've had the pleasure to be associated with Keio University, and in particular Keio SDM, System Design and Management, since 2008, when Keio SDM was founded for the 150th anniversary of Keio University. And so I want to thank especially Shirasaka Sensei for his friendship and support over the last 12 years. You see some pictures here, so I really enjoy being outdoors with my family. I think in Japan, the Matterhorn is very famous, and I had the pleasure to spend much time there as a child. The other picture you see on the upper right is the James Webb Space Telescope, which is hopefully going to launch next year. It will get us a very close look into the very beginning of our universe and the formation of the very first galaxies. So my master's and PhD was on this project, which is actually where my interest in complex systems started. I also briefly want to mention to you, you notice the logo in my background and the background of Brian Sensei. This logo represents our laboratory at MIT. It's called the Engineering Systems Lab. And the logo can be interpreted in different ways. For example, the Earth, the Moon, Mars, and beyond. It's also the 4 groups that have joined together to form the Engineering Systems Lab, including my group on strategic engineering. There's a system architecture lab. There is a group that studies system safety as well. We can also think of this logo as decomposition of a system from the high level to the lower level. And finally, we can think of this logo as going from the present into the future. So from strategy to implementation. In the lab, we do research on complex socio-technical systems. We teach classes in topics like system architecture, system optimization, and road mapping. And our goal is always to have impact, to improve these systems both on Earth and in space. And so we encourage you to go visit the website and explore a little bit what we do. And we're also essentially supporting and running the SDM program at MIT, which is a sister program to KO SDM. This view is familiar, I think, to many of you. This is the greater Tokyo area, which is still the largest city in the world, the largest urban agglomeration in the world. And I think there's no better picture to show what the challenge really is when you look at the Earth and a large urban area like Tokyo at night. You see the illumination, you can see the traffic, you can see the electrical grid, and you can see the footprint of human activity on our planet. And that footprint is growing, and it's becoming more interconnected and more complex. And I think this is what we talk about when we talk about Society 5.0. It is both the physical layer of our society, like we can see in this picture, but it's also the flow of information that is generated by the physical layer of our society. And understanding both the physical and the information layer and how they relate to each other is the core challenge behind Society 5.0. So in this first session, what I'd like to do is discuss some definitions and then focus really on systems thinking. If you're not familiar with it, systems thinking is just one of the ways of thinking about the world. But we think it's a very important one, and that's why we spend time on it. We'll also discuss architecture, and then I will spend some time on 3 systems: the communication system, the transportation system, and the energy system, because those 3 are particularly important, and they're mentioned extensively in the book on engineering systems that some of you, I think, have been able to take a look at. And I will finish on figures of merit, and then turn it over. We'll have a short break, and then turn it over to Professor Brian Mosier to discuss stakeholders and stakeholder analysis. If you have any questions during my session, please write your questions in the chat, and we will do our best to answer them either during the session or after the session. And Brian, are you? Can you hear me?
Yes, I can.
So if you don't mind monitoring the chat, and if there's something particularly, if something maybe you can answer directly in the chat, or if it's something particularly that you want to bring to my attention, then please do so, and don't hesitate to interrupt.
かしこまりました。
Arigato. So I want to also start with a quote here of a gentleman who has been really a big inspiration, not just for me personally and us at MIT, but for the field of engineering systems. And that is Chuck Vest. Charles Vest, who unfortunately passed away several years ago, but he was the 15th president of MIT. He was also the president of the National Academy of Engineering in the United States, and really a very visionary person. And so this is a quote from him where he talks about macroscopic engineering. And this is another way to say engineering systems. It's designing, operating very large systems, like what you saw in the previous picture. And so he says, imagine the excitement of working at the frontiers of macroscopic engineering, the domain of larger and larger and more complex systems in all of these domains mentioned here: energy, environment, communications, healthcare. And you will see that one of the things that is happening is that these domains that used to be very separate from each other are increasingly being interconnected in new ways. And that's what makes our work very interesting, but also challenging. What we are observing is that system complexity is increasing over time. And that's undeniable, and I will show you some evidence that this is true. And it's very, very important because a lot of our traditional ways of thinking, traditional ways of analyzing and managing systems are not able to keep up with this increasing complexity. Why is complexity increasing? For different reasons. One is that we are, we're infusing new technologies. We have higher expectations in terms of performance and resilience. And you will see that many systems are shifting from being more centralized to becoming more decentralized. And this is also a driver of complexity. So here's an example from my home domain, which is aerospace engineering, of this increase in complexity. This picture shows you on the x-axis complexity, which we measure in a quantitative, rigorous way, and it's normalized between 0 and 1. So 1 is the most complex engine, aircraft engine, that's currently on the market. And the y-axis is performance, in this case, fuel burn, or 1 over the fuel burn of the engine. So the higher, the better. And so you can see that this relationship is very, very striking. Every % of improvement of performance in today's aircraft engines gets more and more and more difficult to achieve. We went from, after the war, World War II, from simple turbojet engines to multi-stage turbojet engines, 1-stage, 2-stage, even 3-stage. We started taking some of the air and going around the core, and this is what we call the bypass flow. Again, 1-stage, 2-stage, and the most advanced engines today have a gearbox. These are the so-called geared turbofan engines, and they're very, very difficult to manage and control, but they're extremely efficient. So we need to think about how to deal with this new world, which has much more complexity in it, but also much higher levels of performance. And we described these trends in a book that came out 10 years ago, but then was translated to Japanese in 2014. And again, I want to thank Shirasaka Sensei and the colleagues, particularly at Keio University, for helping with this translation. My understanding is that the book is sold out currently, the physical book, and I'm hoping that we can either do a reprint or make an ebook version available to you if you have not gotten. It's a fairly short book, and I don't think it's too difficult of a read, but I think it summarizes a lot of the messages from today. When we look at the facts about our world, they are quite startling. The human world population has tripled in the 20th century from about 2 to 6 billion. And there's an office within the United Nations whose only job it is to predict the evolution of the world population forward. And of course, there's a range of uncertainty, but roughly, I think it's fair to say we're headed toward 10 billion humans on this planet. The United Nations keeps revising these estimates, but it looks like we might be at about 9 billion by 2050 and about 10 billion by the year 2100, by the end of this century. Most of that growth will occur in Africa, in Asia, and Latin America. And of course, this is all happening while our climate is changing. I encourage you to go to this website, co2now.org. And the first time I gave this talk, about 10 years ago, or a version of this talk 10 years ago, the CO2 level was 390. And now it's about 412. And so that's a 5% increase in the CO2 level in just 10 years. And so this is something we really have to think about and worry about. It's one of the, maybe the biggest challenge of our generation and the generations to come. Like I mentioned, systems that used to be clearly separated are beginning to interact in new ways. And that's good because we get better performance, better efficiency, and also sustainability could be helped by that. But there are downsides, such as cascading failures and poorly understood emergence. And I will be discussing what we mean by emergence. It's behavior that's new and difficult to predict ahead of time. And so in this world, our traditional way of thinking, monodisciplinary, you could say, well, I'm a mechanical engineer, I'm an electrical engineer, I'm a computer scientist, I'm a biologist, I'm a lawyer. That's fine. Of course, we need to understand certain domains well, but it's not sufficient to just work in our domains. We need to think bigger. We need to connect both the technical world as well as the social world together in an organic way. And if you think about the word complex in English, that word actually has roots in Latin. And so in Latin, complex means complectere, which means what? It means to braid or weave together, as you can see in this picture. So the technical complexity in red and the social complexity in blue are being interwoven and interconnected together. And we'll come back to that in just a couple of minutes. And so the definition then, which we talk about in chapter 2 of the book, we talk about what are engineering systems. Well, they are a particular class of systems that have both high technical and social complexity. So only high complexity on the technology, but a very simple organization does not qualify as an engineering system. It's really both technical and social complexity are high and interconnected with each other. Additionally, these are systems that fulfill important functions in society, like transmitting information, transporting people and goods, providing energy, healthcare, of course, with the COVID-19 crisis, which is global. And it's one of the reasons why we are only virtual in this seminar. These are the kinds of systems that we're talking about. It's also a very interesting field of research. And to illustrate what I mean, how do you know when you go from a simple system to a complex engineering systems? It's when you have both high technical and social complexity. And so I mentioned to you, I'm from Switzerland originally, and Japan, of course, is also very good at timekeeping. We'll talk about timekeeping again. So on the left, you see a mechanical watch movement, which is complex. It has, on the order of 150 parts, but the technical or organizational complexity is not very high. So this would not qualify as an engineering system. On the other hand, on the right side, you see the electrical grid of the United States, which is a complex system, both technically and organizationally. And so to grasp and understand these systems better, what we want or what we need is called systems thinking. And so I'd like to spend some time now on systems thinking, but before I do, I just want to pause for one minute and see if there's any questions or comments in the chat so far.
Nothing so far, Ali.
Okay, thank you. So I will proceed and discuss systems thinking. So systems thinking is not the same as thinking systematically. So having, an organized way to think about things in general. It's thinking of things as systems. And so what is a system then? A system is essentially a set of interrelated entities. They could be physical entities, they could be informational entities, but the key is that these entities have relationships with each other, and together they perform one or several functions. And the functions that emerge from these interactions are greater than the sum of the individual parts. So you know, it's not 1 + 1 = 2, but 1 + 1 = A or something like that. So it's not straight mathematics in terms of addition of entities. It's mapping from the form domain to the function domain. And fundamentally, it's about the entities and the interactions amongst them, understanding them together as a system. That's what systems thinking is. And the key, the magic word, if I may say so, and maybe the most challenging concept, is the idea of emergence. That because you put these entities together in a particular way, you get a behavior and a function that you wouldn't otherwise get. That's called emergence. And I'll give you some examples. And I'll start with, you know, I think a very simple example, but a compelling one, which is, let's take sand and a funnel. So the idea is that we take sand and we put the sand through the funnel. What do we get? Well, we get the function of timekeeping. So if you looked at the sand separately and the funnel separately, it's not easy to predict that when you put them together, you can actually use the sand going through the funnel at a very specific rate as a way to measure the passage of time. That's emergence. Here's another example. And I actually, while I was in Toulouse in 2018, so this is the French national soccer team. While I was in Toulouse in 2018, France won the Soccer World Cup. I'm sure you remember, that's only 2 years ago. And when you look at this picture, what do you see? Well, you see a set of individuals, soccer players, and they are the entities of the system. And together, they produced something amazing, which is they brought back the World Cup to their home country. And so performance as a team was an emergent property of that system. Now, that was very positive for France, for sure, but emergence can also have a dark side. So this is an example of emergence in a complex software-enabled electromechanical system like the Boeing 737 MAX. Of course, we're just now getting this particular airplane back in the air, certified again. But as you know, there were 2 deadly crashes of the MAX due to, we can say, a combination of factors, including poor design, insufficient resilience, and insufficient safety of the MCAS system, which was included in the design as a way to make the airplane safer, when in fact it made it less safe. And so this is an example of poor or negative emergence. And then we also have emergence in natural systems. So this is a hurricane or a typhoon, as you call them in Japan. And of course, typhoons can be very, very damaging. And in fact, in the English language, the word emergency is very closely related to emergence. An emergency is when we get a situation or a behavior that's fundamentally, in this case, undesired, that is not easily predicted as a result of the interaction of the system elements, in this case, the ocean, the atmosphere, and the land. And so the key ideas or concepts in systems thinking are that we have function that emerges from the interaction of the entities of the system. We have performance, we have safety and reliability, which are life cycle properties that we will discuss tomorrow in more detail. And we have emergencies. But of course, among these, the emergencies we would like to suppress. Function, performance, safety, and reliability are fine because those create a benefit. And what is benefit? Fundamentally, the benefit from a system is the value that it creates minus the cost to create the system, maintain, and operate the system. So we'll talk a lot about value, and Professor Moser will talk a lot about value as being a key thing that needs to flow in a stakeholder network in order for that network to remain stable or even grow. So the benefit of the system comes from its function, its performance, its safety and reliability, and ideally zero emergencies, or as few as possible. And so what we have done and what we do in engineering systems and systems engineering, systems analysis, is we often don't work immediately with the actual physical system, but we create abstractions of the system. We remove or hide characteristics or details of the system that are not essential features to understand the system. And we focus on the essential features in the system to create an abstraction. And this abstraction of the system is used to design the system, to operate the system, to analyze failures of the system. And so, and that's really what's important. And there are more than one correct abstraction of a system. In fact, there are probably infinitely many abstractions of a system that you can think of. And so if we think about us, we have 89 people on this Zoom call right now. How do we abstract ourselves as a group? Well, for example, we are a learning organization. We are here to learn, to listen with each other. So we're primarily a learning organization. Or we could be a physical group or a virtual group or a political organization. And so that's what we mean by abstraction, is simplifying the view of a system to its core, to its essence, to its essential features. And so for emergence from a design system to be understood, we need to now go a bit deeper and look at form and function of the system. And so separating clearly the form of the system from the function is one of the most important things that we teach in system design. And it's one of the most important things that I think not just engineers, but people who are dealing with complex systems need to understand. So the form is what the system is. Okay, it's physical and informational embodiment. It's the shape, configuration, arrangement, or layout of the system. And it is what's eventually implemented. The function is what the system does. It's the set of activities, operations, and transformations that cause, create, or contribute to the performance of the system. It's the actions for which a thing exists or is employed. And it's what eventually happens. Okay, so emergence, the way we've defined it so far, comes from the functional domain, not from the form domain. It can be triggered by the form domain, but it goes through the functional domain. And so to illustrate this, I want to go through some very simple examples with you and look at form and function. And then we'll do that again for a set of systems, and we'll dive deeper in the next step. So form and function of this thing that's shown here, and those of you who are electrical engineers, of course, have an unfair advantage. What is shown here is a so-called amplifier circuit. And so we'll decompose the circuit in a minute, but fundamentally what we have is the form, which is this amplifier circuit, which is shown with a set of electrical engineering components. So we have resistors, we have an op-amp, and we have a ground. And so the amplifier circuit is the instrument. And if we have to build it, this is where the cost of the system is accrued in creating the form. Now the question is, what is the function? What is the function of the amplifier circuit? So let's see in the chat, if you have any suggestion as to what the function is, you can just write it in the chat. Maybe we have some, I'm pretty sure we have some electrical engineers here. Brian, I don't know if you can see anybody writing.
I'm looking at waiting. It's a blank canvas for the moment.
Anybody from electrical engineering? What is the function of this circuit? Let's see.
No takers.
No takers?
Maybe some music lovers.
Should I call on somebody, maybe? Or should I not do that? Let me try. On team 5.
Now we have
We have an answer now.
more answers.
Already.
What is it?
Amplifying the signal from both Fukuyama-san and Minami-san.
Wonderful. Thank you very much. So the process is the process of amplification. So the amplitude of the system is being increased, and that's the process. So a function has both a process and an operand. The thing that is being changed or affected by the function. So the way we would read this is that the amplifier circuit, which is shown here, amplifies the signal. And the benefit of this system, very simple system, comes from the amplification of the signal, which is its function. Okay? So now let's look at a social system, a team, a design team. The team is shown here. And of course, the cost is, the salary of the team. They're the instrument. What is the function? Well, let's assume this is an R&D or a development organization developing a new design. Okay, so developing the new design is the function that the team performs. So the benefit comes from the function, which is to develop a new design, which is done by the team, and this is where the cost accrues. Okay, let's look at an example. Let's see if we have anybody who remembers their human physiology class or any medical doctors in this group. So this schematic here shows you the lungs, the heart, the veins. So essentially the human circulatory system. What is the function of that system? So again, please, if you would use the chat, maybe we get some more responses this time. And if you look closely on the diagram, it actually tells the story. Brian, do we have any responses?
We do. We have three answers. What's interesting is some are specific to the circulation of blood or pumping blood, but someone specifically calls out the oxidization or input energy to blood. One way it's described. So oxygen is another answer.
Yes. So I think the last answer, is probably my favorite, which is that the function here, of course, is to supply oxygen. But if you're looking closely, that's not the only function. That's just one of the functions of the circulatory system. And this is, you see the oxygen here entering the lungs, supplying this to all the tissues and organs in the human body. The energy, though, comes from a different source. The energy comes from the digestive system and eventually gets transformed into what's known as ATP. And so the oxygen is used to combined with the ATP to, power our bodies. But if somebody would have written to remove waste in the form of CO2, for example, you see the CO2 is exiting the lungs here. That would have been correct as well. So removing carbon dioxide would have also been a perfectly correct answer. And so you see that our biological systems are amazing because they are so multifunctional. Okay, so now let's try this for a fairly recent example in Japan, which I am only mildly familiar with, which is that Toyota announced earlier this year, or last year, I should say, in January of 2020, that they are building a new city called the Woven City. And you can see the picture, it's beautiful. The city is here. Mount Fuji is in the background. And here's a link to an article about this woven city. And so my question to you is, why are they doing that? In other words, what is the form? What is the function? What is the process and the operand? Any suggestions, please, in the chat. And I will try to annotate. Maybe we start with the form.
Function as can you see the chat, Ali? It's universal acceptability to mobility. So I think increasing universal access.
Okay. Is the city only about mobility?
Well, the form is noted as mobility infrastructure, or the function is universal acceptability. So it has to do with affecting acceptability towards these modes of mobility. Another answer from Fukuyama-san is just future city.
Yeah, I think at this point, we haven't really decomposed it yet. I will just write future city. I think I like it because it's quite general. It's quite general.
Another person wrote, Minami-san wrote, smart city as form rather than function.
Yeah.
So, and others wrote the process as smart and the operand as service. Another is functionality is mobility for all. And again, the form being the city itself, the smart city.
Yeah. So I lost my mouse. Let me recover my mouse. And so what I would say is that there are different ways to interpret it, and this is why it's so important to be very clear about what the purpose of that system is. Let me see if I can.
Let me add. Fujita-san wrote, "The form is life, the process is smart or smartness, and the operand is service."
Very good. So let's try this. Future city. The process, I would say, from my reading of the article, is to experimenting, meaning learning from, and the operand would be new technologies. Maybe that's too general.
Well, Minami-san also wrote that the process is focused on building a brand new technology, but with citizens.
Yes, so the co-design, essentially.
Experiment, yeah.
Yeah, absolutely. So you see this even at this level, this exercise is not so simple. It's worthwhile really thinking about these terms. Okay, so let's continue. So this was the first task. The first task was to understand essentially the form and function of the system. Now the next step is to understand the entities of the system. In other words, what's inside the system. And in order to do this, we need to think holistically, and we need to define the boundary of the system. So what's inside the system, what's outside the system. And so focusing on what's important, defining abstractions for the entities, their form and function, and then defining the boundary of the system and its surrounding context. Again, this sounds very, very simple, but in many, many systems, it's quite difficult. And depending on how you set the boundary, you can come to quite different insights or conclusions. So let's do that for our three examples. So we have our op-amp, our circuit that we looked at before, and its function is to amplify signals, as we said before. But now what we're doing is we've added here the functional decomposition. So we are now looking at sub-functions that are necessary to amplify the signal. And so we have the op-amp, which is this element shown as a triangle. it's amplifying its input voltage difference. So the difference between the two terminals is being amplified. We have two resistors, and the function of a resistor is, of course, to limit the current and set the gain. How much amplification are we going to get out of the circuit, which is a function of the ratio of the resistors R1 and R2. And so now we're starting to decompose the system, and each entity of form of the system has its own subfunction. If we think about the circulatory system, we have the heart, it pumps the blood. We have the lungs, they exchange oxygen and CO2 with the surrounding air. And we have, of course, the capillaries, which exchange as well the oxygen and CO2 with the organs, so on the other side of the lungs. And of course, we could go much, much more detailed. We could have 2, 3, 4, 5 or more levels of decomposition until we arrive at very small and very basic entities or building blocks of systems. And then our team, of course, is made up of individuals. So in this case, Amy, John, and Sue. Or if I look at our list of participants, we could have Takeshi. We could have, let's see, on team 3, we have Yoshiko. And then in team 6, we have Masako. Okay, so you would make up the team, and this team has a name, for example, Team X. And each of you has a different function on the team. For example, interpreting the requirements, developing the concepts, and then evaluating and approving the design. Again, we could go much more detailed here, but I think hopefully this gets the point across. So let's come back to our example of the woven city and see if we can do this. So the city form was our future city. Our system function was experimenting with technologies, new technologies. And so how do we decompose the future city? Let's use the chat again. What are the elements of the future city?
Standing by.
Don't be shy.
Here we go. Mobilities. Entity form is mobility. Infrastructure.
Okay. These are very general. Can we be a little bit more specific?
Energy, communication, healthcare, robot, people.
People, that's good. Robots, yeah.
Sensors.
And
energy grid. Home.
energy.
AI. Finance.
Yes.
Buildings, houses, roads, car, government, automation, digital twin, university.
Okay, wonderful. So all of those are great. I only have room for 3 here, so
vehicle was also added.
Okay, let me maybe add vehicle. It's a little bit easier than robots have so many different potential functions. So the function of people is either living and working in the city. What is the function of the vehicle or vehicles? Is transporting, right? Moving around. And the function of the energy grid or electrical grid is energy providing, right? And so all of those are sub-functions, entity level functions of the overall system function of future city, which is experimenting with new technologies. And of course, this is a very, very small set of the ones you mentioned, which were all great, by the way. And so we would continue this process and then go another level and maybe another level until we've really captured the essential entities of the system. So that was our second task in systems thinking. The third task is to now think deeper about the relationships among these entities, so their form and function. And relationships are foundational for systems. The relationships can be formal, as in the structure, or they can be functional, as in the interaction. For example, if we have an exchange of energy, information, or matter between elements, that would be a functional relationship. If two elements are connected structurally, that would be a structural relationship. And so the idea is we have our system boundary, we have our system entities, we have structural and functional relationships, and we have also relationships or interactions between systems inside or entities inside the system and entities outside the system. And so identifying those relationships is our third task. And this will reveal both the formal structure. So for example, even if you think about a social network, as you see here, that's a formal structure. So what is your friend network? Or functional interaction. This is an example of a performing arts group like the Tokyo Ballet Company. And so you can see there's no physical connection certainly in this picture between the ballet dancers, but together they have a functional interaction from which emerges a message or the performance, the artistic expression of their performance. And so if we look at the three examples that we looked at for the amplifier circuit, we now have our resistors, our op-amp, and we have the structural and the functional relationships inside the system boundary. And then we have our input and output terminal. One of them serves, of course, as the reference voltage against ground. Our Team X, our design team, gets inputs, for example, from marketing. And so marketing performs an analysis, and requirements are being transmitted from the marketing team to Amy, who interprets these requirements for the rest of the team. And then the output of the team, which is the design that they suggest, is passed on outside the system boundary of the team, for example, to the operations team. And then in the circulatory system in the human body, we have the air on one side, which is outside our system boundary, and it essentially supplies or dissolves or absorbs both gases, oxygen and carbon dioxide. We have the exchange of these gases inside of our body through the lungs, the heart, and the capillaries. And then on the other side, again, inside our body, but outside the boundary of the circulatory system, we have our internal organs and tissues which absorb the oxygen and then exude the carbon dioxide. So that's essentially the next step in the third step in systems thinking. And so the relationships amongst the entities are different. When we look at these three examples, the entities are different, the patterns of relationships are also different, but the fundamental building blocks are often can be brought down to the fundamental sciences of biology, chemistry, computer science, sociology, and so forth. So we know that when there is a functional interaction, there almost always is a formal structural interaction as well. And the functional interactions are what we need to understand to understand emergence. And that is the last step in systems thinking, is understanding or predicting emergence. And when does emergence occur? It occurs when the functional interactions within the system boundary produce a new functionality, which is more than just the sum of the parts. Okay, that is fundamentally emergence. which is a difficult concept, but which is an essential concept to doing systems analysis. And so if you think about it, when we looked at the circulatory system in the human body, the combination of pumping blood, exchanging oxygen with CO2 with the air in the organs led to the function, a higher level function, the emergence of supplying oxygen. Interpreting requirements, developing concepts, and evaluating and approving the design led to the emergence of developing a design. And so we can look at very simple engineering examples. So this is for the electrical engineers amongst you. What do we have here? We have a resistor on the left. That's the element of form. And the function of a resistor, of course, is to hold the current proportional to voltage. And then we have a second electrical circuit element, which is a capacitor. And what is its function? Well, the voltage in a capacitor is proportional to the change of current. So the rate of current change over time. We put the two together, and what do we get? So we have a very simple circuit here with a resistor and a capacitor, which in this case is grounded. What is the emergent function of this very simple circuit? Again, if you want to write in the chat.
This is tough, Ali. I remember studying this 30 years ago.
Well, of course, Brian, you are a 6.3 graduate and not a 6.1 graduate, so I think you have a partial excuse. So the answer is that this is actually... Do we have an answer in the chat?
Smoothing, filtering, or limiting the peak.
Yeah. Very good, very good. It's a low-pass filter. This is a low-pass filter. And how could we predict that? Well, that's what the history of engineering and science has taught us, and we've invented new systems by combining these fundamental building blocks. So by combining a resistor and a capacitor, we get the function of, filtering out high frequency content from a signal. This is for the more mechanically inclined. We take a bar or a rod, we combine it with a pivot, and we get a lever whose function is to amplify force. Okay, so the structure enables, but emergence comes fundamentally from the functional interaction. Very, very simple examples. A little bit more complex. Brian, I think this is more in your territory. This is one of the very first algorithms anybody learns in computer science. This is sorting a list. This is the bubble sort algorithm, where you have essentially nested loops that loop over an array of items. And out of that, you get a sorting function. So emergence can be predicted a priori by precedent, meaning you've already built or seen a similar system, by experimentation, or increasingly by modeling. But for unprecedented systems, so systems we've never built before, modeling and experimentation are not easy. And human reasoning still is essential, even in the age of AI, I will argue. And so the framework of systems thinking and the procedure, the 4-step procedure, supports human reasoning. And that is really the goal and the real art in systems thinking. So let me stop here for a second before I talk about, the last part of the lecture. Let's see if there's any questions or comments about the 4 steps in systems thinking.
Yes, Ali, there's one question. Can I think that emergence is always designed in system engineering? Emergence is used to describe something unexplainable, such as human consciousness or deep learning output.
Yeah, so our ambition is, of course, that all emergence is predictable, but the reality is that it's not. So emergence captures both known behavior, desired behavior, designed behavior of systems, and undesired, unknown, surprising behavior in systems. And I did give you some discussion on the history of the progression of aviation, and it's very true that aviation today is a very, very, very safe. If you look at the numbers, it's we could argue that it's the safest form of transportation, but it wasn't like this in the beginning. And so with every accident that we've seen in aviation, we learned about emergence. And the learning about emergence was built into the next generation of aircraft design. It was also built into regulations and operational procedures. And so over a long period of time, close to not quite 100 years yet, maybe 80 years of commercial aviation, the system has become better and better and higher performing and safer because we have mastered emergence.
Another question, Ali.
Mm-hmm.
How can we choose one single set of abstractions for functions and forms of a complex system, like a smart city, which potentially has an infinite number of hierarchical goals and different viewpoints and interpretations for it?
Yeah, that's a really good question. So typically, you will not have only one single abstraction. You will, for the same system, you will create multiple abstractions with different layers of detail or decomposition, and for different stakeholders or different purposes. For example, for your customers, when if you produce a product, like I noticed that. We have a participant from Honda Motor Company. It's Hideaki Ohara. Are you here? From Team 7? Ohara-san, are you here with us?
He answered yes in the chat.
Thank you, Ohara-san. Thank you for joining us. So Honda creates many products, but very good cars, very good vehicles. The customers get the user manual, for example, shows you the features of the car that are essential for the operator. But a lot of the details inside the system are hidden from the user because it's unnecessary. And so we create different abstractions with different amount of information for different stakeholders in the system. And finding the right level of abstraction, the right level of detail is very challenging. But we never create only one for everybody. I think that's a fair statement. By the way, in digital engineering or model-based engineering, our goal is to have only one source of truth. So all the information about the system, its components, its functions, its interactions, to have it all in one database at one place from which we can derive different representations for different purposes and customers. That is a big trend, I think, in model-based system engineering, and a lot of effort is being spent on this. It's not finished, but I think we have made progress. So coming back to the lecture in this slide, I told you that complex comes from Latin and means braiding together. And previously I said it was technical and social. Another way to think about it is what we're braiding together are these 4 perspectives that we discussed in systems thinking. So scale and scope, function and structure, or function and form, and then temporality, thinking about the evolution of the system over time. Because so far, we've taken a more static view of systems. But if we really want to understand systems, we need to understand time as well. And so I wanted to give you a kind of example of that many of you might be familiar with, since volcanoes are very famous in Japan. This is Pompeii, the city of Pompeii, which was covered by Mount Vesuvius in a very famous eruption, which happened very quickly and covered the entire city and essentially froze the city in time. And the point I want to make is that engineers are not the only systems thinker. You should be a systems thinker in any profession, including, for example, an archaeologist. So imagine that you're the first person to arrive at Pompeii and it hasn't been excavated yet, as it's shown in this picture. You will ask at least these 4 questions. How large is the site? Is it 1 by 1 kilometers, 10 by 10 kilometers? So you define the boundary of the city. That's the scope. As you find different structures, you will ask, well, what purpose did these serve? Was this a residence? Was it a marketplace? Or I know in Japan, onsen is very, very popular, a hot bath. The Romans also had baths. Was it a bath? Was it a military facility? Was it an armory? The next question is, how was the city connected? What is the structure, the form? Was it a circular city? Did it have a regular grid? Was there a main axis? How was the city connected to neighboring cities? Those are all structural questions. And then, of course, the 4th question is about temporality and the role of time. How did the city change over time? And of course, in archaeology, what that means is going deeper. Every layer of depth in the excavation gets you further and further back on the timeline. So the point here is a good archaeologist is also a good systems thinker.
Ali, there's one question from Minami-san. Do you have any tips on how to arrange and select partial functions to lead to an emergent whole?
Yes. So the general idea is that you develop your functional decomposition inside out, meaning that you first focus on the key operand. What is the system? What is the purpose of the system fundamentally? Once you understand the purpose, you understand the core function or sub-functions that are needed to fulfill the higher level function. Once you've identified that, around the sub-function, you have supporting functions. And these supporting functions can be found and enumerated to decompose at the level below. And then you repeat that multiple times, depending on the complexity of the system, until you've reached a level of abstraction and detail that is sufficient for your purpose. Was that clear?
To me, it was.
Okay.
Very clear answer, and we'll be showing examples of this over the next 2 days.
Yeah, very good. So let me proceed. So one question that often comes up is, well, how do we classify systems? Is there a taxonomy of systems? And so you see on this chart different attributes that have been used to classify systems. Degree of complexity, which branch of the economy or sector does the system belong to? The states of the system. Is the system controlled by humans or is it fully automated? What we found is that perhaps the most useful way to classify systems is by their function, the functional type of the system. That really, I think for most purposes, is the most useful way to think about systems grouping or classification. And so based on systems thinking, you can see on this grid or matrix, the columns are different operands. And shown in gray here, this is classical engineering, technical systems. They operate on matter, energy, and information. And then we have the fundamental processes or functions, which are to transform, to transport, and then to store or house. We don't talk about that a lot, but that's actually a very, very important process. And so transforming, transporting, and storing matter, energy, or information, this gray part of the matrix, That's classical engineering systems. However, recently, in the last, I would say 50 years, we have expanded that. So we have money and we have living organisms, humans and animals, which are also treated separately as operands because they're very important and we can't just consider them as innate matter. And so if you think about it, technologies that are in this column, money, are what we call fintech. And technologies or systems in the most right column are what we call biotech. And we've also added two more functions, the function of trading or exchanging, and then the function of control or regulation. And so this gives us a 5x5 grid, which we can use to classify systems, engineering systems, but we can also use it to classify technologies. And I've shown some examples here. I haven't fully populated it, but we can find examples for every one of these cells. And so I'm going to just focus, if you go back here for a second, on three of these, which is, again, the three spines in the engineering systems book. And so we go back in time, not too far, but we go back to, the time of the Industrial Revolution. So this is the 18th century, and then the 19th century, which is, of course, in Japan was a very important time with the Meiji, particularly the Meiji Restoration was a very important time where Japan really transformed itself to bring a lot of these systems into society. And what we had was the time of what I call the great inventions, the automobile, the telephone, the light bulb, but and a lot of these, this is the year of the first patent. A lot of these inventions were just not accessible to the larger population. There was not really a full system yet supporting them. It's only over time that automobiles required highways as we scaled it up, and it became available to a larger fraction of the population. The PSTN, that's the public switched telephone network. And then, of course, the light bulb led to the electrical power grid. And then moving into the late 20th century and early 21st century, we get into multimodal systems. So transportation can be done by air, by rail, by highways, and several other means. Communications can be done by, the classic telephone network, which is increasingly, I think, being retired, the internet, voice over IP, satellites, and then energy. We have a mix: solar, wind, nuclear, fossil fuels, still important. And so this is the brave new world that we're in, the world of engineering systems. And I'm just showing you transportation, communication, and energy, but there are other spines as well in our society. For example, air transport. We'll talk tomorrow a bit in more detail. And then very important currently with the COVID crisis is the healthcare system. So vaccines were first invented in 1796. Imagine that. But the whole system we have today with R&D in the life sciences, hospitals, healthcare, all of that has grown up over the last century and a half. And we have emergence and interconnections, interrelationships in all of those systems. So the boundary of the system becomes more difficult to define. And so let me just give you three examples, and you'll hear about some of these examples, especially the stakeholders involved with these systems, from Brian in the next lecture. So, for example, Takanawa Gateway. So the whole rail or public transit network in Japan, which is one of the very best in the world. And Takanawa Gateway Station is a new element, a new entity that is being developed in that particular system. And we're very fortunate at MIT that we are collaborating with JR East and actually developing some new ways of thinking about modeling, simulating, visualizing the whole design space around transport hubs like Takanawa Gateway, which is not purely about transportation. It's also about retail, It's about non-transportation functions. Another example from the communication spine that is happening right now is the deployment of satellite constellations. We had a first generation of satellite constellations in the late 1990s, but there's a revival of that. And so the Starlink constellation, which is being deployed by a company called SpaceX in the United States, is probably the largest of these. As of 3 days ago, they had launched 955 satellites. And when fully operational, this system will give high bandwidth internet connection essentially anywhere you are on the planet. And then finally, the third example is nuclear power stations, which I know is a big topic in Japan, especially after 2011. Another example of a country that has invested heavily in nuclear power is France. So this article and this chart here shows you that within about 20 years, France went from almost zero electricity production from nuclear to over 80%, 85%. And this system was created deliberately by the government of France as a way to reduce dependency on fossil fuels, which, of course, has financial, but also political and geopolitical reasons why this was done, which are not so different from the reasons that Japan developed nuclear power. So the last, let me stop here for a second and see if there's any questions or comments before I touch on the last point. I'm not sure I followed 100% the political discussions in Japan about nuclear power. Has there been a decision about the future of nuclear power in Japan now?
I'll let one of my Japanese colleagues answer that.
Or is it still ongoing discussions?
It's both complex and complicated, I will say, but the answer pretty much is no.
A no meaning it's still under discussion?
In Japanese, we would say,
I see. So it's an interesting system then. So let me continue and just talk about figures of merit, which are really important because most of the discussion we've had so far on systems has been more, let's say, qualitative in nature. This is a famous quote by Lord Kelvin, who was a professor in Glasgow in Scotland, and has contributed a lot. The Kelvin temperature scale is named after him, contributed a lot to the development of the field of thermodynamics. And basically what Lord Kelvin is saying in this quote is that unless you can quantify what you're observing about a phenomenon or what you're observing about systems, if you cannot quantify the phenomenon that you're interested in, you may have some knowledge, but the knowledge is of a meager and unsatisfactory kind. And so understanding systems both logically, qualitatively, and quantitatively is very important. And the way we do that is to use figures of merit. And so I want to give you an example of figures of merit. This example here is quite famous. It's from a book called The Singularity is Near, written by Ray Kurzweil, who's actually a graduate of MIT and has written a lot about the future of technology. And I don't want to debate here whether the singularity, as he predicts, is going to happen. But what I do want to discuss is this graph. So this graph shows you on the x-axis time, and on the y-axis, the points are different processors, computer processors, of different technologies like electromechanical, vacuum tubes, transistors, ICs, integrated circuits. But what's really interesting to me, and it should be interesting to you, is always look at the y-axis. What is actually being represented here? And so this says calculations per second per $1,000. What does that mean? Well, that's a figure of merit, right? So y of t is the number of calculations per time, unit of time. So it's the speed of computing divided by the cost of computing. So essentially, it's looking at how much computational power can you acquire for a $1,000 investment of money. And we can see that, this is logarithmic, so it's extremely impressive. And even though the points are discrete, if we have enough points, we can actually approximate that with an exponential curve, which comes in two flavors, either discrete or continuous. So in discrete time, for example, we can look at 1 year increments. We have some initial performance, why not? And we multiply that with 1 plus r to the t. T is time, discrete time in this case, and r is a kind of annual rate of progress. Or we have a continuous version of progress on this figure of merit, which is y0 or y0 times e to the kt. Okay, and then you can see here how you transform from the discrete to the continuous parameter that drives progress. What we find, it's astounding, is that computing using this particular figure of merit has improved by an average of 37% over the last 80 years or so. It's very impressive, and it continues to progress at this rate. Another example, going back further in time, is the steam engine. And so if you look at the progression of steam engine technologies, here using the figure of merit of efficiency of the engine. So how much useful work can you get out relative to the amount of energy that you supply? Energy, for example, in the form of coal. We know how much energy coal has. And so how much of that can we extract to perform useful work, as shown on the right side? This, by the way, was the original Newcomen engine in England in 1712 that didn't have a condenser, so it wasn't a closed loop. But you see impressive progression, but at a much lower rate, at a rate of about 1.7% per year. But over 250 years, that leads to a significant improvement in efficiency. And so I did mention the functional view of classifying technologies and systems. And so we can then attach and define for each system or technology in this matrix different figures of merit to understand how performance and other behaviors or functions have improved over time. And so a question I often get is, how do you construct figures of merit? Well, you start with what we've essentially done, the function. So I'm using here transforming matter as an example. Transforming matter takes in inputs. It consumes energy. It requires a controller, a processor. It produces waste, and it produces useful outputs. So steel making is a good example of that. And so using a representation of the system as such, we can define many different figures of merit. Some will be more interesting or important to some stakeholders than others. And so I encourage you in your work for Society 5.0 and the work of the DADC to define figures of merit and quantify the performance and the life cycle properties of these systems using real figures of merit. And they come into different categories like performance, productivity, efficiency, sustainability, and other life cycle properties that we'll discuss tomorrow, competitiveness, and life cycle properties. Again, I will defer to tomorrow's discussion. And then here's some examples for each of those categories of figures of merit. Many of these you're familiar with. So for automobiles, acceleration, the yield in agriculture, efficiency for steam engines, sustainability in power plants, so CO2 emissions per electricity unit generated. In banking, the cost per customer transaction. And in aircraft, the mean time between failure of components. what's very important also, and I'm personally a stickler on this point, is that you always define units of measurement. Always define units of measurement when you define figures of merit for systems. Okay, so I know that was a lot of material, and I think we're pretty much on time. I will say this as a summary. So this was an overview of our engineering systems, which are complex socio-technical systems that fulfill important functions in society. Systems thinking is really critical to understand and predict emergence in these systems. There's a step-by-step way to do systems thinking, to analyze and define systems abstractions. And just to remind you the 4 steps. Step 1, you identify the system form and function at the system level. Step 2 is you identify the entities of the system. So what's inside of the system, you decompose the key entities in the system. And by doing that, you also define the boundary of the system. In step 3, we then identify the relationships between the entities of form and function. And step 4, which is the most challenging, is we predict the emergence. Then we discussed briefly figures of merit as a way to not just have a qualitative, but also a quantitative understanding of how our systems perform and what behaviors they exhibit. And eventually, do they actually deliver value, which is benefit at cost? And in order to understand value from systems, we can't do that just looking at the physical or technical layer of the system. We need to understand the stakeholders. So who's involved in the system as a designer, as an operator, as a customer, as a beneficiary? And understanding stakeholders deeply is the topic of the next lecture. So I will stop here. I think we have about 2 minutes for some questions or discussion, and then maybe we take a very short break between my end of this lecture and Brian. So let's see if there's any comments or questions.
And I would encourage people to ask directly if they are comfortable.
Dozo, please.
So Satake-san asks, are entities made up only of forms and functions? Does it possibly contain anything else?
No, we don't think so. We think that entities are form. Form can be physical, you know, like a phone, but an entity could also be an idea or a concept or a piece of information. So it's an object that exists. And functions are the processes that act on the elements of form, on the entities. And that's it. Really, if you think about it, physical systems, artificial systems, biological systems can all be represented by elements, entities of form, and entities of function which act on the elements of form.
Okay, thank you. Thank you very much.